Hello, I'm Xinjie from Tongji University, and I'm very happy to share our research with you here. Our research is about pattern recognition and prediction of bending active thin sheets via artificial neural networks. Bending active is an efficient approach to fabricate curved geometry. The biggest problem regarding bending active structures with thin sheet is the difficulty of predicting the accurate deformed geometry with the consideration of the structural performance of large deformation. AI can be suitably applied in the pattern recognition of very complex structural behavior, such as the highly nonlinear large deformation of the bending active structure. This paper investigates the characteristics of the bending active deformation of a 1.2 meters long, 0.2 meters wide rectangular aluminum sheet with 1 mm thickness as a standard prototype. The degree of freedom is restricted with only 3 parameters, referring to the translation of the edge. To provide enough accuracy of the neural network to extract patterns in the complex large deformation of thin sheets, a large amount of data is required in the training process. In this research, the acquisition of data is simplified and achieved by the finite element analysis with the Cromba 3D plugin in the Grasshopper environment. The dataset contains 3,000 samples, representing different combinations between deformation and boundary conditions, of which 2,800 random ones are used as the training set and the remaining 200 as the validation set. Each column is a training sample, with row 1 as the serial number of the sample, and rows 2-5 as the record of the boundary conditions, and the next rows 6-129 as the record of the coordinates of the sampling points that represent the deformation of the aluminum plate according to the sequence of the initial mesh of the planar thin sheet. 2 neural networks are designed, one to find the corresponding deformation condition by inputting the positions of the nodes that record the shape, and the other to obtain the position of the node that records the shape by inputting the deformation condition. Here are some of their hyperparameters. Through the test of the forward prediction of the bend geometry based on given boundary condition, among the nodes predicted by the neural network for predicting deformation, 80.01% of the predicted sample points have an error of less than 10 mm, and 96.29% of them have an error of less than 20 mm, with an average error of 8 mm, which is only 0.67% of the plate length. In the test of the backward prediction of the possible boundary condition, the average error in predicting the initial translation of the neural network is 1.6 mm, which is only 0.4% of the average range of all sampled translation. The results show that the proposed method and tools have good accuracy in both the inference of initial conditions and the prediction of deformation. With artificial neural network as the main approach, a fast and both accurate predictions is achieved based on 3,000 input finite element analysis outcomes. At the meantime, not only a forward bending prediction but also the backward prediction of the possible boundary conditions, which will lead to an arbitrary bend form, is achieved. In the future research, real physical bending tests will be taken with more materials. It is expected that the artificial intelligence could be taken as an important tool for understanding material and fabrication, which could improve the performance-based architectural design. Thank you for your listening.